Rust, which is Python's new performance engine. Well, I wouldn't call it, I mean, you can't call it new. It's not new, but it is definitely being used more. In this case, check this out. This actually inspired me. This is what I want. This is the plan for today. It's what I want to do. I want to try it out. It's been a while since I've had used Rust libraries inside of Python. So being able to, be in the Python coding language, which is a simple language, and then being able to call out to a library that has been pre-compiled in Rust, and then gaining and netting the performance of Rust, which is very close to C, but also you get the concurrency safety as well, and the memory safety built into Rust, which is really powerful. And so that's what we're going to do. This article that just came out earlier this week inspired me to try it again. This is something that I've done before in the past, and it's just something I want to try. And I actually want to benchmark it. I want to see like a native Python list and say, Harsha, hey, how's it going, Harsha? Hey, dude, how's it going? Hey, dude, we're gonna do a thing right now. We have about an hour, I think. Wait, do I have an hour? Let me double check. I want to make sure I have enough time here, because this is gonna be a fun one. We're gonna take Rust. We're gonna compile a library in Rust, and then we're gonna call to it from Python, and then we're gonna compare Python's performance with like maybe a simple multiplication a function. We'll put it in a for loop and we'll benchmark it, and then we'll call to Rust and we'll see how fast that is. I'm very curious to see what the performance difference is going to be. So Rust usage for Python's extensions surged by 22% in some year, in just 1 year, as developers chose memory safety and the C-level performance over traditional approaches, right? So like PyTorch, which is, the premier, OpenAI uses it for ChatGPT for their AI training. libtorch is written in C, and it calls out to the GPU. And a lot of gaming engines are also written in C for the performance. Now, Rust gives you the same level of performance, but you get extra memory and concurrency safety. And so that's why everyone is moving to Rust instead of just using C, because it's a lot easier, because the compiler will find a lot of the problems. Now, to be fair though, there are more modern C compilers that do a really good job. They do a really good job of catching a lot of problems and challenges as well that you'd run into, like that would cause memory leaks or undeterministic behavior. So they are getting back. They are doing good, but Rust is just a lot more friendlier from a more abstractions perspective. And you don't have to deal with the concurrency safety, so it's really powerful. So this is what I want to do. It's say, people who are building Python libraries are doing it in Rust, right? So like Rust usage for Python binary extensions jumped from 27% to 33%, a 22% increase. Just in a year, which, tells you that, hey, everyone's, Python's great because it's really easy to program in, it's accessible, and you can do a lot of things really fast. The problem is it's slow. It's very slow. Hey, Lorax, hey, good to see you. We're going to see if we're going to do a speed run here. We've got about 30 minutes. We want to build a Rust library, a Rust binary that we can call from Python and import it like a Python module. So I've got I did this before. I did this a couple of years ago, but I want to do it again. I want to do it now. So we have a little bit of time here. NumPy is great. NumPy is actually written in C, which gives you the performance of a really powerful, fast compiled language. But then you get to use Python, which is a higher level language, and it's a lot easier to use. It's more approachable. You want to do NumPy, right? You've already got NumPy. You scikit-learn, which is great. It's like a traditional machine learning library. And then you want to jump into things like PyTorch, which is libtorch, written in C through C bindings. But we're going to do a Rust binding today. So we have 27 minutes. We can do this. We can make it happen. You can do it in 27 minutes. So I have to follow these instructions. And actually, I think I have to install Rust as well. Install Rust. All right, here we go. Let's get Rust installed. I need to do this because we've got it running on a server. Obviously, I don't want to... If you've run the Rust compiler before, it takes over your entire computer. And since we're streaming live and we're encoding video, we don't have the CPUs available. So let's get our server up and running here. So we got our server. Let's get Rust going. Proceed with standard installation. All right, we'll get Rust into there. And then I think we need to make sure that we've probably got 3.7 or later. I'm pretty sure. Our Python is good to go. So we have a few things that we have to do. So what we're going to do is we're going to follow these guys. We're going to follow the easy. We're going to do the easy mode. And then I want to benchmark it if we have time. So easy mode should take 5 minutes and the benchmark should take 20. All right, here we go. Oh, let's see here. So source home. Okay. Oh, interesting. I just want this usually done by running. Okay, one of the note dot cargo. Okay. I think we're good. Let's see if Rust is Rust installed? No. Okay, so let's see. Maybe we might have to do a couple things here. Is that gonna do it? No such thing? Okay. I might have to restart my shell, which is no big deal. Okay, I'll just restart the shell screen. There we go. All right, so CD. Okay, let's go into the RustPy CD RustPy directory. I created a directory. Screen. Here we go. Get our GNU screen going. Now is Rust there? Yes, we have it. Rust, we did it. Okay, so Rust is installed. So now Python dash version. Let's see. All right, we're on 3.12. We're good to go. And then Rust C dash version. Okay, Rust. I'm pretty sure it's Rusty version. There we go. Okay, we're good to go. We've got Rust. We've got Python, but we need to make sure that we follow these instructions. Okay, so we're going to create a virtual environment like that, and then we're going to source the virtual environment. Okay, and then we're going to install Maturin. Let's see, whatever Maturin is. Okay, looks like we got Maturin installed. Okay, now we're going to initialize Maturin, Py03. Okay, excellent. So what that did was it created a directory for us with our project. Let's open up. I'm actually kind of curious. Let's look at this cargo. By cargo toml. All right, so we've got ourselves a RustPy edition name. The lib, it's a lib RustPy, and we require Py03, which is going to be our bindings. It's going to help us create bindings for, I think maybe through FFI, I'm not sure, for Python to call into Rust. So that. If we look at, actually, what is this? What's this PyProject.toml by PyProject? What is this? I don't know what this is. I haven't seen this before. This is new. Do I have to do anything with this? I'm not sure. I'm not familiar with that, but let's see. Let's move on to this. Here we go. Okay, so now we've got our tutorial set up. We should be able to just run cargo build, and I think it should create the Python module for us directly. Let's see if there's anything else in here instruction-wise. So yeah, so we've got our Py3, and then we've got what we have here. So we've got a PyFunc, right? So, and a Py module, which is going to help us understand when we're building, right? So these annotations, this will help us create those bindings that we can call into. So RustPy, interesting. Oh, interesting. Okay, so we've created a module called RustPy, and we're adding the function SumString, which is sum as a string. So it'll combine the two integers, and then look, pi of g plus h. Basically, I mean, good news is we're in Rust world now, and so Rust has a much more strict compiler. And in the previous stream, we were looking at PyTypes, or sort of PyType, which is a type checker, a linter that prevents you from accidentally coercing and doing things that you shouldn't do. But good news is we're in the Rust world. So I think we should be able to say cargo build. Yeah, there it goes. Running some cargo builds there. See, finally run Maturin develop. This will build the package and install into Python virtual inf. Oh, neat. Oh, that's really neat. Okay. Oh, so cool. All right. So we're at the, okay, let's do this. All right. So let's close this. We don't need htop anymore. Get rid of that. All right. So Maturin develop. Build fail. Virtual inf and conda prefix are set. Please unset one of them. Okay. All right, we'll just unset conda prefix. Unset. Done. Okay. Is it going to work now? All right, perfect. Okay, so it's building our Py03. It's going to build our project, and it also installed the module I believe, called py_rust. So we should be able to say Python import py underscore or rust underscore py. There it goes. There it goes. Isn't that cool? Okay. So we should be able just to be able to run, I think, this function on it. So rust underscore py, and then we say dot. Let's see here. Let's get the dot in there. And then that should actually, yep. So what that did was it calls out to Rust. Rust does the math. It converts it into a string, and then it serializes it back into Python world. So we did it. We just did it. We took a Python, we're in a Python runtime, and we built ourselves a Rust module that is usable inside Python. And we just ran it just now. So isn't that satisfying? It is so satisfying. Can I rerun mature and develop? And then it just rebuilds it? Okay. So what we can do now, this is where I'm excited. This is what I'm really excited about. We can, I'm going to just split the screen here so we have the top and bottom. I'm going to open up the source, and I want to create a new function. And this function is going to be, we're going to benchmark, say, we're going to do a for loop with multiplying some numbers together. So like we'll just do a for loop to multiply numbers. I think that's a really good idea. Okay, so we'll pipe from here, get that. Actually, we'll just do fn benchmark multiply. Okay, and we'll have we'll say pi module. Oh no, pi function. There we go. And then we can import that here. We want this benchmark multiply. We want benchmark multiply, and that. What is m? Oh, I think that should be. I think that's it. I think we're good. Oh wait, no, we need to do a pi result. It's got to be a pi result. And does the pi result care if it's a U size? I don't know. Let's find out. Cargo build. Let's make sure it builds. And then we'll see. Oh, see, it's got a problem. I see. Okay, so we have to wrap in a result. Okay, let's try it again. Okay, so it built just fine. But what about Maturin? Is Maturin going to work? Okay. So now we have a multiplication function that we wrote in Rust. Really simple, right? It's really simple multiplication function. Just combines two variables, and then we should be able to call that in Python. And then we can also. So I actually want to write a Python, a little Python file. Let's do that here. All right. So let's do test.py. All right, so we got test.py in our, where'd it go? Oh, there we go. Now we should see it. Okay, cool. So let's do import, it's called rust py, and then we can run rust, not hello, but let's see, it's going to be rust py multiply. What was it? Where is it? Here it is. Benchmark multiply. Okay. And we'll go 1, 2. Actually 2, so we know that it's actually going to be 4, right? Because this should be 4. Should return 4, yeah. Okay. Now I can just run Python test py. Wait. Do I need to oh, I didn't even print it. Okay. Let's do result equals and then print result. Just spell result. Res. Here we go. Now I should literally be seeing 4. Okay, perfect. All right. So now we can benchmark this thing. So I want to benchmark it in 2 ways. We have 17 minutes. Well, 16. We've got 16 minutes left. We can benchmark it in 2 ways. One, I want to see how fast it is to call a Python multiply and how fast it is to call a benchmark multiply from Rust. And then I want to see how fast it is to do a for loop to multiply some numbers inside of Rust and then over here as well. But we'll see how far we get. We're almost there. We're almost there. So we have our benchmark. I want to just call it multiply because it's really simple. keep things simple. There we go. Multiply. And then I'll just change it down here. Okay. And then we run our Maturin. I think we have to rerun Maturin develop again. And now we can run Python test. There we go. Yeah. Oh, so we have Zemiki. Hey, you are like my brother. Wow. All right. There you go. Rakashit. This is interesting. It is, isn't it? It's interesting. So what we're doing here is we're calling Rust. We're calling into Rust from Python. So we've got a Python runtime, and we're compiling a Rust library. I'm very curious to see. Multiplication is one of the most difficult compute things. The next most difficult would be division, but I don't want to deal with floating point numbers right now. So I just want to do some, Zemiki. This is actually really cool. I'm excited about this. So we've succeeded right now. We have our Python code here, and you can see it at the very bottom of the screen. So right up here, right up here, you can see the first one, test.py, where it says test.py, which is right over here, test.py. This it's only 4 lines of code, right? I think, yeah, it only goes to 4 lines. Well, let's make it 3 lines. There you go. Even better. And so what this does is it calls into Rust, and it acts a pre-compiled library that does multiplication. So it's going to be a lot faster in Rust because it can do better in Rust, which is really cool. So boom, there we go, right? Calling into Rust. I love it. So we just done it. What I want to do is benchmark it. So I want to do def my own multiply. So that is multiply in Python. And then this is Rust multiply. So what I can do is I need a benchmark function. Def benchmark multiply. Let's see if that works. No. Let's see here. Good, but run the code. Oh, yeah. But run the code. Yeah, so this is the... code run. See, there you go. It's running. We're running it. It's always going to return 4. So I'll make it a bigger number. Let's do 20 by 20. Let's see. There we go. Let's return 400. I'm pretty sure that's 400, right? So there you go. So we're calling from Python. Hey, for study. Hello. How's it going? For study. We are currently playing with Rust libraries, and we are calling those Rust libraries from inside Python. And we're doing this for performance reasons, mostly because I was inspired by this article. It got me kind of excited. Just reading the headline alone, it was really neat. I'm like, why don't we do this on a regular basis? Why don't we write more code in, code that's, requires more compute and more power in Rust, and compile it and then call it from something like Python, because it reduces your tech debt, really. Because it makes it a lot simpler, because you want to keep things in a language that's easy to maintain, and that is definitely Python. Although you would say Rust is similar in that. So Rocket Sheet Ninth, I can't wait to see the benchmark. Me too. So I've got 12 minutes. That's what we got. We got 12. Now what are we making? We are currently making a benchmark. We want to say how fast Rust is versus Python, but calling from inside Python into Rust. That's what. Just use Rust. Like, why are we even using Python? Like, what's the point? Well, here's the deal. Rust. Look at the syntax. Just let's step back for a second. I know we only have like 10 minutes here, but let's look at the syntax. So, you Batty, you're saying the really good point. Just use pure Rust. Why not? We should totally do that. Here's one argument, and also why we've got PyTorch with libtorch. Look at the complexity of Rust. See how there's so much annotations and extra and macros and these question marks all over and these brackets. There's a lot. There's just a lot there. And then you compare that with, say, Python, and it's just a lot simpler. I mean, see here at the screen, we've got this. It's so simple. It's super clean. Yeah, we're doing Python and Rust. So we succeeded in calling Rust from inside a Python runtime. And that's basically what we did here. So I'll zoom up. So we created ourselves a little Python library that was compiled from Rust. And then we're calling into it and we're multiplying a number and printing. And so, right, so I'll do it again. Boom, 400, 400, 400. So now you're seeing Python calling into a Rust library. Isn't it cool? So now this is, we're going to benchmark it. So we have about 10 minutes left because then I got to run to a meeting. Rocket Sheet. So basically, instead of the team learning Rust, they just use the Rust wrapper. Yeah. See, there you go. There's another good reason. So with Python, it's simple and clean. And so you don't need to worry about it. And the team would only have to learn Python. And they'd use the Rust wrapper for better performance. Sounds good, but I think that beats the point of Rust. A C wrapper would do fine. Yes, you could do the same thing with C, and that's what a lot does as well. At my company, PubNub, we use a lot of Rust, but we also have some Python and things. But we're doing what someone else already mentioned here. That might as well just use Rust, which is just use Rust, plain Rust, and that's what we do. But we're having fun right now. We're playing. We want to see how it works, and we want to try it, and it's neat. It's just neat to be able to call, a Rust library that you compiled and call it from inside Python. So that's why I think is neat. WSP, which one is the main language? So you can do it either way. So you can call Python from Rust and Rust from Python. But I think it's more interesting to call Rust logic from inside Python because you net the benefit of a benchmark. Yeah, I want to do the benchmark. We're running out of time. We are running out of time. So we only have, we've got 8 minutes and 30 seconds. Okay. So here we go. Let me get rid of that. So we've got ourselves the Rust multiplication and we've got ourselves the Python multiplication. So let's do we want to benchmark. Let's see here. Benchmark multiply function. Let me make sure to get this right. Multiply function, and we do that with like a for loop. Well, I guess we could do it like this. All right, let's see if that works. All right, so I don't like this approach. I want to do something different. I want to let's get rid of that. Oh, space. Let's do a for loop. Here we go. That's a little bit much. We don't need to do that many. And then we need to say a start equals. We need to import time. I think start time dot time, and then end time, and then print. Perfect. Okay. Let's see if that works. We're just gonna do that really quick. See if that works. And then we need to actually call the function. All right, def benchmark. So we'll call it here. Go to the bottom. There we go. Boom. All right. What we're doing is we're doing simple benchmarking. We're going to do a simple benchmark. So we're going to benchmark. This will be Python multiply, and then we'll do the Rust multiply. So here we go. Okay, Python multiply and Rust multiply. This will do the Python multiply, or actually, is this the Python? Yeah, I think this is the Python multiply. Yep, Python multiply. Okay, perfect. Wow, you are good at this. Why not JavaScript? You can do it in JavaScript too. It's really cool, and you can even use WASM. So you can compile Rust to WASM container, and then it's actually a really, really good question from Hamid. Why not JavaScript? You can do this in JavaScript as well. Just take the Rust library, compile it to a WASM library, and then you can import it in JavaScript. And you can do the same thing. And you can also use it in a web browser or Node.js or Dino runtime. So that's something you can do. We're doing Python right now. Yeah. So yes, and then DWSP, you also recommend wrapping in C, which totally makes sense. We're doing Rust because I think it's neat. And we use a lot of Rust at PubNum. Oh, okay. We're running low on time here. So let's get the benchmark, time multiply. Okay, we did it. We just ran. All right, so let's do a couple more here. See if we get that running. Okay, we can do a few more. For loop, get a big more. Okay, let's do another. Let's make it bigger. Okay, There we go. All right, so that is 320 milliseconds. That's 320 milliseconds for the Python. And we'll say this for, boom, that number of times. Okay, which is a lot. That's 10 million. 10 million iterations. Is it really? Wait. 1, 2, 3, 1, 2, 3. Yeah, that's 10 million iterations of multiply. And that's actually pretty fast for Python. I'm actually kind of impressed at how fast that is. So let's try it now with making this into the Rust version. Bro is saying Python is easy. Yeah, I mean, yes. It is compared to Rust. I mean, look. I mean, you see the syntax. So like here, check out the syntax. This is right here that you can see on the screen. We're jumping back and forth. This part right here, this is Rust. It's a little bit more advanced. Just a smidgen more. It was regularly do 1 billion. It's like a standard benchmark number. Okay. We'll do 1 billion. Well, see, the problem is I'll do 1 billion, but I only have 4 minutes left, and I have to run to a meeting. So we have 4 minutes left, and I need to do the other version of this function, which is going to be the Rust multiply. Rust. Here we go. Rust, and then we need to call this here. Perfect. We'll just say rusty.multiply, and then boom. Okay. So this is 10 million time taken. So we'll say Rust, and then this other one is Python. Python. Perfect. Okay. So we just do this, and then we go Rust. Perfect. All right. Now all I have to do is press enter. Boom. Then we'll go up here to our Rust version. There we go. Okay. We're going to run it again, and then we're going to see, oh, yes, Rakesh, you called it. You figured it out. Why'd the Rust version take 4 times longer? And it is because IPC calls. It's basically we're calling out to the library, and that takes latency versus just having it in Python native, which is just running in the VM directly. So that's why it's slower. So what you need to do is you need to put the for loop inside of the Rust code here. So we have to do the for loop here in this code. So we have to say for, here we go. Let's just do it like this. And then, no, I don't want any prints. We want to do a multiply A times B. And then I will say underscore equals. We say let underscore, equal. I forgot. Let's, not let. That's not let. Let's see here. What is it? It's a def. How do you define variables again? It's been so long. U size. Let's see here. Oh, putting it inside changes everything. Yeah. See, I think we're gonna see. I think we're gonna see a win when we do that. So we'll just do it like this, and then we don't need the for loop down here. We won't need the for loop. Let's call it like that. Okay. So now I need to build. Okay. No extern. Let's see here. 1 second. Let me double check. See what's going on here. We're almost done. We only have like 30 seconds left here. Okay, so that built. So what we want to do is figure out why this is having an issue. 1, 2, 3, 4. How about we just, I wonder if we can throw it away. I don't know if we can. I don't know if it likes that. Expected U size. Is there a Golang version of this? There probably is. Yeah, there's a Golang version. Mute var k. Let k equals mute. Okay. K equals. There we go. Okay. Build. Okay, it looks like it built. And then we want to do an underscore to get rid of the warning. Does it like that better? No. Let's see here. Let mute I. I. Okay. I think maybe, will that be good? No, it doesn't like that. How do we do this? It's building, it's fine. If this is intentional prefix with an underscore, oh, because we don't ever use it. Oh, okay, so we'll do that so we get rid of the warning. Okay. I'm only 1 minute and a half late for my next meeting. Okay, so Maturin develop. Here we go. All right. Now all we have to do is test.py. There we go. Look, we did it. So we just benchmarked calling, a multiplication in Rust from Python. And then we called Python in native, the same benchmark that did the same thing. And we see the result is a lot faster in Rust. We did it. Congratulations, guys. Isn't that amazing? That is so cool.